So, dear students, we can start our lecture. So, in previous lectures, we understand different conditions for calculating maximum negative shear, positive shear, bending moment at a section, and absolute maximum bending moment, and absolute shear force, etc. So, what are the different loadings we are going to have in our problems? So, first one, point load. So, single point load moving along the bridge. Second one, UDL. UDL, and also the UDL will be shorter than the span. The length of UDL will be lesser than the span. Third one, UDL longer than the span. The span length is minimum and the length of loading is very large compared to the span. Fourth one, two point loads, that is two wheel loads, two axles will be there. So 2 point loads traveling from left to right. And fifth one, multiple point loads or series of point loads. So point load, single point load, it will be given with some magnitude 10 kilonewton or something. UDL, the span of the bridge is larger than the UDL given value. Okay, and UDL longer than the span. That is, you consider the span of the load is very large compared to the span of the beam. Next one, 2 point loads. Two wheel axle loads are considered, can be it is 50 kilonewton, 40 kilonewton with a fixed distance of 2 meter. So this two load only going to travel along the beam. Then multiple point loads, it can be accommodated with the UDL also. So the span distances between the individual loads will be given like this. So you have to consider this loading system traveling along the span. So now all problems we are assuming, and if the problem will be given in left to right direction. So all the problems we are going to solve by considering left to right travel. Okay. And what are the conditions? Simultaneously we can discuss for maximum negative shear. So what will be the condition? We have to calculate RB value when it is negative shear force. So RB value means if it is having head and tail, because the point load will not have any head or tail. It is a single point of contact. But UDL will have head and tail, and the multiple point loads also will have head and tail. If it is head and tail, for maximum negative shear force, place the head. Place the head. So it is a general criteria we have to follow. For maximum positive shear force, we have to find RA and place the tail of the load. Place the tail of the loading. Okay. Next one, for maximum bending moment, when the case of UDL shorter than the span, we have to divide the UDL with the same ratio as the section divides the beam. We already have seen this criteria. If the section divides in the ratio of x and L minus x, the same ratio we have to divide the loading by considering some unknown distance A. So C minus A. From this, you can find out A value. You can find out A value. So you then mark the section and place the loading as A and C minus A and find the bending moment under the section XX. So this is one of the criteria. This is all about UDL shorter than the span. Okay. Coming to series of point loads, for maximum negative shear and positive shear, we have to give some trial by moving the loads on left side and calculating the SI ratio, that is WC by L minus WI, where WI is the load which moved towards away from the section. C is the distance between the critical load and the section. The load which moved away from the section is the critical load. So C is the distance between WI and the section. L is the span. And SI ratio, if it is positive, you have to give some other try, another one try to get a negative value, because positive sign represent increase in shear force value, and give another try. And if you get negative, consider the previous one. In first trial itself, if you get negative value, you should not move this load away from the section. You place again the load at the section and calculate the RB value. Calculate the RB value and also confirm whether the shear force at this section is only RB, because again I am explaining, if the section is like this and there is no load in this span, the shear force at XX is equal to RB. There is no problem. If the section is here and the RB, I am telling it is RB. If one load is here, W1, then shear force at XX equal to RB minus W1. So we have to very much careful about this. Not in every case the RB is directly the shear force. If there is any one of the loading along the span, we have to deduct RB minus W1 for getting the shear force. Similarly, in case of maximum positive shear also, we have to follow. We have to place head or tail according to this criteria. If you want to maximum negative shear force, place the head and move one load on right side. In case of maximum positive shear force, place the tail, move one load along left side. Okay, maximum absolute maximum bending moment. Okay, next one we can see the maximum bending moment. Maximum bending moment at a section. So what is the ratio? LR ratio. So WL by X minus WL minus X by, sorry, WR by L minus X. WR by L minus X. So WR means load on right side. WL means load on left side. So we have to move the loads away from the section. You should not place the load on the section. It is very important in case of maximum bending moment. You should move the load away from the section and calculate WL and WR and the span ratio X and L minus X. If you are getting positive sign in the first trial and a negative sign in the second trial, then the load moved at this point is the critical load. So place the critical load at this section, and calculate the maximum bending moment. Next one, absolute maximum bending moment. So what is the criteria? Consider all the loadings, even included with the UDL, and mark some resultant at a distance x where r equal to total load, and taking moment about the first load, taking moment about this load, you rotate all the loads with the corresponding distances and also the opposite direction resultant into x distance and find out the x so that you can identify the position of the resultant and identify the critical load which is near to the resultant. You will have x distance, so you can able to identify which load is nearer, whether this point load or this UDL. So you identify the critical load and you measure the distance between the critical load and resultant and you divide it by 2 and place the critical load and the resultant equal distance from the center. So we need not place the resultant for further calculation. We only need to place the critical load which is at the half distance evaluated from this calculation. And if you place this load, then automatically other loads will be placed because the fixed distance is available. Then once the load is fixed, then you can calculate the bending moment under the critical load. Bending moment under the critical load. You should not calculate the bending moment at a section or at a center. Bending moment should be calculated under the critical load. So these are all the very important points in unit 1. There is nothing other than that. So we can solve number of problems with the understanding of these concepts. So we are going to start from a simple problem. Okay. So I have taken the values randomly. That is, I have taken 30-meter span and also going to take 20 kilonewton point load. And I'm going to consider, so the problem statement, consider the section. You can give at 8 meter or 10 meter. I'm going to consider the section at 8 meter. Calculate the shear force values. If it is commonly asked the shear force, we have to find out negative shear force as well as positive shear force. And also bending moment at the given section. This is also for the given section problem. And calculate the possible questions can be asked. Calculate the absolute maximum positive shear and absolute maximum negative shear and absolute maximum bending moment. So these are all the positive questions can be asked with this loading. So first of all, we have to keep in mind that the ILD diagram for the shear force is this. Throughout this unit, we are going to use this diagram, and ILD diagram for bending moment is this. So this is ILD for shear force variation and ILD for BMD variation. Then the ordinates are x by L and L minus x by L. This is negative shear force, this is positive shear force. Here the bending moment ordinate is x into L minus x by L. The major advantage of influence line diagram is we can calculate the ordinate only with the geometric properties. If you have the length of the beam and the sectional details, we can calculate x by L and L minus x. And I have plainly given the section at 8 meter from the left support because it should be mentioned. Some other problem you may be mentioned with from the right side. So you have to convert the x distance from the left side, which is for your convenience. So here I have mentioned 8 meter from the left support. Okay. So I am going to mark the sectional details 8 meter so that 22 meter remaining. Okay. Next I am going to draw directly the ILD for shear force. So shear force ILD, and what is the value of x by L? 8 by 30, L minus x by L 22 by 30, because this is x, this is L minus x. You need not simplify the values. Okay. Then further you have to apply the load, because only one load is there. There is no two wheel loads or multiple axle loads or UDL. It is only one load. So directly you can place the load on this section. Next one, maximum positive shear force equal to, this is the positive shear force diagram. So the maximum ordinate is ILD ordinate, that is ILD ordinate into load. This is the general formula. ILD ordinate is 22 by 30, loading is 20. 22 by 30, loading is 20. Next one, maximum negative shear force. The same formula, ILD ordinate into W. The negative diagram is this. So 8 by 30 into 20. So this is the calculation for maximum positive shear force and negative shear force. So using the calculator, it is 14.67 kilonewton. Next one, 8 by 30 into 20. 9.76 kilonewton. 8 by 30 into 20. So it is 5.33, because if you sum up this loading 14.67 and 5.33, it should be equal to the applied load 20 kilonewton. If you add up this, 20 kilonewton. Okay. So this is maximum positive shear and negative shear calculation. Next one, the VMD variation. VMD variation at the given section 8 meter and 22 meter is, this is the general diagram, and the ordinate value is the formula x into L minus x by L. So x is 8, L minus x is 22 by L is 30. So calculate the value 8 into 22 by 30, which is 5.87. Okay, and you superimpose the load 20 kilonewton and the maximum bending moment at 8 meter from support A, which is equal to 5.87 into 20. So it is totally 117.33 kilonewton meter. So this is the bending moment value at the given section. Next, we are going to calculate absolute maximum positive shear, maximum negative shear, and absolute bending moment. So the general condition for absolute maximum positive shear is, actually we have drawn this diagram like this. This is at a section itself. If this positive diagram extends up to A, this will be the maximum shear we can obtain. Okay. So when you get this maximum ordinate, when you place the load directly at the support A, you can get the maximum shear force, positive shear force at A. So the what is the maximum ordinate of the shear force means it is equal to 1. So ILD for maximum positive shear force is this, and you superimpose the load 20 kilonewton. Obviously, you will get 20 kilonewton as the positive absolute maximum positive shear force. In the same way, absolute maximum negative shear force, if you extend this negative diagram, you will get the maximum value at B. When you will get the maximum value at B, if you place the load directly at B, then you will get the maximum value at B, and I am going to draw in the negative side because RB is negative. So the overall ordinate is 1 and applied load is 20 kilonewton. So what is the value? Absolute maximum negative shear force equal to 1 into 20. You can put minus. So minus 20 kilonewton. Okay. Next one, absolute maximum positive shear force, absolute maximum bending moment. So what is meant by absolute maximum bending moment? I have already told that it is the maximum of maximum bending moment, possible bending moment value along this any section, along any section. So we know that the center of gravity of the load as well as the center of the beam should be located at a single point. Here we are having a point load. The center of gravity lies itself within itself, and the center of beam is our beam is 30 meters, so 15 meter and 15 meter. Then this load to be located over the center. The center of gravity of the load should be located over the center of the beam. So our load is 20 kilonewton. And draw the ILD diagram. What is the formula here? X into L minus X by L. What is X here? 15 meter. L minus X is also 15 meter. If you substitute this, you will get the formula. If you substitute X equal to L by 2, L by 2 into L minus L by 2 divided by L. So L by 2 into L by 2 by L, which is equal to L by 4. If you multiply with the loading, which is equal to WL by 4. What is the formula for the, what is the case for this formula? That is simply supported beam with the central point load will have the bending moment ordinate as WL by 4. So you can directly mark as L by 4, or you can substitute X equal to 15 and L minus X equal to 15 divided by the total span equal to 30. So 15 into 15 by 30. So which is 7.5. 7.5 is the ordinate at the midspan. This is the ILD for bending moment, and you superimpose the load 20 kilonewton and you calculate absolute maximum bending moment equal to 20 into 7.5. So it is 150 kilonewton meter. So this problem is a very simple problem. It is only for your understanding. This problem can be asked with 2 marks only. Okay. If you observe this bending moment value, absolute bending moment value 150, in previous case, we have calculated the bending moment at 8 meter from A. It is only 117.33 kilonewton meter. So if you consider some other section, you will get the value, but it is always lesser than this absolute maximum bending moment. Okay. With this simple problem, and you recall all the conditions to be applied to place the load in a beam for different conditions, maximum shear force and bending moment. And we will come up with another example in next video.